Our last example will be investigating the amount of energy in an unusual shaped waveform, or maybe it's a very usually shaped waveform called the boxcar. And we'd like to make it of width tau and height 1. Again, this is a time domain waveform. And if we're going to make it width tau and centered, it'll have to go between negative tau over 2 to positive tau over 2. The question is, given that waveform, find the Laplace transform. So let's first see if our intuition gives us any help. Spoiler alert, it won't. If we take a look at this box, we can see that there is a non-zero DC value. So at DC values at 0, it should be greater than 0. And if we were to build this box out of cosine waves, somehow they have to all cancel each other out for all values of time greater than tau over 2 and less than negative tau over 2, and somehow make the top of the boxcar even at 1. Man, there is just no intuition here. So we're going to have to just grit our teeth and write it down. So there's our definition of the Fourier transform. This is always true. There's no way I see Euler's identity helping us since we're not dealing with sines and cosines. So I don't see any way out of this but just putting this in. Now, one nice thing is that it's pretty easy to see what happens to the limits. Since this is 0 outside of these limits, we only need to integrate between negative tau over 2 and positive tau over 2. And in that region, f of t just becomes 1, so this whole expression drops down to this. We can evaluate this as if it was e to the negative k anything. We take the reciprocal of what's up here and write it outside the integral, and then the rest is evaluated for t, running from minus tau over 2 to positive tau over 2. Seems like it might get a little bit long, but I think we could do it. We've got our 1 over negative j omega. And when we substitute in tau over 2, we get e to the minus j omega tau over 2 minus e to the minus j omega. We got a minus and minus, that's positive tau over 2. Well, we've got a minus out here, and we've got a minus here. So I'm going to do is switch these inner components and then take away this minus. It's the same thing as multiplying this part by a negative 1 and multiplying this section by a negative 1. So that gives me 1 over j omega. And then I'll make this minus and this positive. So that flips the two sides. That gives us e to the j omega tau over 2 minus e to the minus j omega tau over 2. Now, where have I seen the difference of two complex exponentials divided by a j? That's right, it was Euler's identities. So now we have a new challenge, which is to make this look like one of these guys. So this is a minus, and it's divided by a j. This is a minus divided by a j. We want to make it look like a sign. How are we going to do that? Well, firstly, we want it to look like 1 over j times 2. So I'm just going to write it down as what I wish it was. I wish it was j 1 over j2. So how do I make this look like that? I'd have to get rid of that 2 and divide it by omega. So now if I multiply these guys together, the 2's cancel, and I'm left with 1 over j omega, which is what I have here. But if I look at just the right side of this, it looks exactly like this part of my Euler's identity. So I know I'm on the right track. Let's see. So far, I've just written down a fancy version of this. Let's see what else I can write. I want to write e to the j omega over here. But the problem is I've got this times t over 2. So I'm going to redefine my omega to be omega tau over 2. And I'm going to do the same thing over here. Here's our minus e to the j omega tau over 2. And now this whole thing is mathematically the same thing as this, but this subpart is exactly the same as this subpart, just with this omega being omega tau over 2. So therefore, I can say all of this has got to be sine of omega tau over 2. Now this is such an important result that we actually give it its own special formula name. We call that this is a sinc function. And in future classes, we'll be a little bit more precise about which portion of this is the sinc function, but in general, it's the idea that it's a sine of a variable divided by that variable. And if we were to graph that, it decays down. You can see it has a envelope that it's decaying. This is why it's decaying down to that envelope. This 1 over omega, this is its envelope of 2. Well, it's 2 over omega. The biggest the sine can never get to is 1, so it's going to decay down with this decreasing envelope. And meanwhile, it's going to be moving up and down. It's going to be oscillating because of the sine. A reasonable question to ask is, what is this value up here? What is it doing at 0? Remember, this is a graph of our Fourier transform. This is omega. If you were to ask, what is its DC component? What is f at omega equals 0? If you try to naively substitute it in 0 here, you'll end up with 2 over 0 times sine of 0, which gives you 0 over 0, which gives you anything. So instead, I want you to recall one other fact, which is the sine of a small number is about equal to that small number. Try it out on your calculators. Evaluate what is sine of 0.01. And it looks like the same thing. If we get a few more digits here, we'll see it's really close. And as that number gets smaller and smaller, whatever number you put in is the same number that you get out with a sine. As omega goes to 0, sine of omega tau over 2 becomes just omega tau over 2, and you get 2 over omega times omega tau over 2. The omegas cancel, the 2's cancel, and you're just left with tau. And that should be intuitively satisfying, because if you go back to your original waveform and say how much DC component is there, that's how much net positive value is there. Well, the area of this is positive tau. Same thing. So let's review everything we've talked about. We started off talking about the definition for a Fourier transform. We said it's this. We said the intuition is that the Fourier transform tells us how much energy there is at any specific frequency of a periodic or non-periodic waveform. We said this is to go from the time domain to the frequency domain. We said you're not going to go the other direction using anything but tables. And the tables that we developed so far are here. And in our last example, we developed one other table transform, which is that a boxcar that's symmetric of width tau has the Fourier transform of 2 over omega times sine of omega tau over 2. These are 4 fundamental and frequently used transforms. And then we also reviewed Euler's identities, which you'll be using a lot in the Fourier transform world.